So here we have an astronaut on another planet, and he's going to throw a rock up in the air with an initial upward velocity of positive 12, right? 15, sorry, positive 15 meters per second. All right, and it's going to go up. Now look, I'm going to draw this as a position versus time graph, so it'll show it as a parabola, right? Because this is, we're extending time. It doesn't mean it's going in a parabola. It just means that I'm showing it that way, all right? So here's our y position, here's time, all right? So it's going to go up, it's going to come down. So you want to know what g is on this planet. This is a weird one, because usually when we say free fall, we know that g is always going to be 9.8 meters per second squared downward. In this case, we know enough other things so we can determine g on this planet. All right, so we know that v naught is equal to 15 meters per second. Now, what do we also know, interestingly enough, no matter what g is? That the velocity here is going to be 15 meters per second downward, isn't it? Okay? So in this case, since we have stuff going up and coming down, by convention, what should we make positive and negative? Since we have up and down, what would you choose? Upward to be positive? Yeah, I think that's a good plan. Okay? So that means that actually when the rock lands, it's negative, or when it hits its hand, it's negative 15 meters per second. Is that going to be significant? May or may not. Depends if you square it or not, right? All right, so now we know that V final is equal to 15 meters per second. All right, and we know what time is. Isn't that 20 seconds? We know it takes 20 seconds. So the bigger G is on this planet, the more or less time it's going to take. What do you imagine? If G is bigger, gravitational acceleration is bigger, it's going to take more or less time to go up and come down. Less time, as G gets bigger. So that means as G gets bigger, time becomes less. If we find an expression, we should expect G to be in the denominator, shouldn't we? All right, so what are the things we have here? We have V naught, we have V, we have T, and we have one thing we're looking for, and this is this special G, this weird G. So taking a look at what we have and what we don't have, what would you imagine is our, is our equation that we would choose? Votet. Okay, we've got all the Votet stuff. All right, so here's our unknowns and knowns. We'll label that, and we'll say formula is equal to Votet. V is equal to V naught plus AT. Okay, and what is our acceleration? So we're really doing A, doing some algebra, and substituting and doing some algebra. We get V is equal to V naught minus GT. Everybody okay with that? And this is a special G. This is not our G. You might want to designate that with a prime or something like that. I don't think you need to worry about it that much. So now what are we going to do? We're going to solve for G, correct? So how we do that? First thing we do? All right, so V minus V naught is equal to negative GT. Now what are we going to do? Divide each side by, how about if we do negative T? All right, so G is equal to negative quantity V minus V naught over T, right? And just rewrite that algebraically as V naught minus V over T. So is it going to be important that V final is negative? It is important. Otherwise, we'd get an answer of 0, wouldn't we? All right. Now we're going to get an answer of 30. So now we're going to do our S, our solution, and we're going to say that G is equal to V naught. What's our V naught? Positive 15 meters per second minus, what's our V final? Negative 15 meters per second. See why it's important? And that's all over T. Our T is 20 seconds, right? Dimensionally, what do you get? Meters per second, meters per second, meters per second on the top divided by second, meters per second squared. We'll get an acceleration. All right, so now G is going to be equal to 30 meters per second divided by 20 seconds is equal to 1.5 meters per second squared. Okay? So in your guess, or in your estimation, you imagine that this planet is larger or smaller than Earth? Probably smaller. Why do you think it's smaller? It's got a lower gravitational acceleration. In other words, its gravitational field at its surface is less strict. Good. Oh, I did want to point out on the previous problem that we selected the positive route for the velocity. We didn't call it negative velocity. The problem number, what was it? 35? 37? Okay, because we took downward to be positive. So in case there's any confusion, as you make this your second problem that you